Everyone is measuring the wrong thing. When people argue about GPU versus TPU, they pull up flops charts, they quote peak BF16 numbers, they benchmark a single matmul, and then they declare a winner. But the actual fight in 2026 is not about flops. It is not even about chips. It is about the supply chain underneath the chips. I work in silicon, and the version of this debate that happens inside the industry sounds nothing like the version on Twitter. So in the next 13 minutes, I'm going to walk you through the 4 layers where this race is actually being decided, and at the end, I'll give you a real answer. Here's the problem with flops comparisons. Peak flops is a marketing number. It assumes perfect utilization, perfect data movement, no memory stalls, no thermal throttling, no networking bottlenecks. In real workloads, especially trillion-parameter training runs, sustained flops are often 30 to 50% of peak, sometimes lower. So when a slide says one accelerator does 20 petaflops and another does 18, that gap is noise. The real war is fought at 4 layers, and you have to look at all 4 to see who wins. Layer 1 is the process node. What fab and what generation of transistor are you building on? Layer 2 is advanced packaging, specifically TSMC's CoWoS, which is the actual supply bottleneck of this decade. Layer 3 is HBM, high bandwidth memory, which determines how much of your silicon you can actually feed. And layer 4 is the system, how you wire thousands of these chips together into one coherent training fabric. Miss any one layer, and the chip is just a paperweight. Let's go layer by layer. Layer 1, process node. Google's TPU v7, codename Ironwood, is built on TSMC N3P. NVIDIA's GB300, the Blackwell Ultra refresh, is on TSMC 4NP, a custom variant of the N4 family. So Google jumped a full node ahead of NVIDIA. That sounds like a clean win, but it is not. Here is what jumping to N3P buys you. Roughly 18% better performance at the same power, or 34% lower power at the same performance compared to N5. Higher transistor density, about 1.6 times that of N5. For a workload that is power limited at the rack level, and every hyperscaler data center is power limited, that's enormous. Google operates its own data centers. Power per rack is the constraint. So Google chose efficiency. NVIDIA chose something else. NVIDIA chose volume. 4NP has been in mass production since 2022. The yields are mature, the IP libraries are mature, the packaging flow is mature, and NVIDIA's customers don't just want the best chip. They want hundreds of thousands of the best chip this year, not in 18 months. By staying on 4NP for Blackwell and Blackwell Ultra, NVIDIA can ship at a volume that an N3 class node simply cannot support yet, because TSMC's N3 capacity in 2025 and 2026 is thin and contested. Apple takes a huge chunk of it. What does this tell you about each company? Google is vertically integrated. They design the chip, they own the rack, they run the workload. So they optimize for total cost of ownership over a 5-year deployment. NVIDIA sells to everyone, to Microsoft, to Meta, to Oracle, to sovereign clouds. So they optimize for time to market and supply elasticity. Same problem, completely different objective function. Neither is wrong. They are answers to different questions. And by the way, the next generation NVIDIA part, Rubin, will move to N3 class. So this gap closes in late 2026. Process node is a snapshot, not a destiny. Layer 2, advanced packaging. This is the part the industry actually loses sleep over. Modern AI accelerators are not single chips. They are multiple silicon dies, compute dies, I/O dies, sometimes a system on chip, plus stacks of HBM memory, all sitting on a silicon interposer, all wrapped together into one package. The technology that does that wrapping at TSMC is called CoWoS, chip on wafer on substrate. Both NVIDIA Blackwell and Google TPU v7 use CoWoS, specifically the high-end variant, CoWoS-L, which uses local silicon interconnect bridges instead of a single giant interposer, so you can build packages bigger than the reticle limit. CoWoS-L is the only path forward for anything past a few thousand square millimeters of silicon plus 8 or 12 HBM stacks. Here is the bottleneck. TSMC's CoWoS-L capacity in 2026 is somewhere around 70 to 90,000 wafers per month. A massive ramp from 2024, but still not enough. Demand exceeds supply by a wide margin. Every leading-edge AI chip in the world is fighting for slots on the same handful of advanced packaging lines. This is why Rubin Ultra, originally announced as a 4-die package, was rescoped down to 2 dies. Not because NVIDIA can't design a 4-die part. They can. But the packaging yield, thermals, and interposer warpage on a 4-die CoWoS-L package at scale in 2026 was not going to hit volume targets. So they pulled it back. Read that again. The world's most valuable company scaled down its flagship product because of packaging, not transistors. Packaging. That tells you where the constraint actually is. CoWoS-L capacity is the gating resource. If you cannot get CoWoS allocation, your roadmap doesn't matter. And right now, NVIDIA, Google, AMD, and Amazon are all in line for that same allocation. TSMC is the kingmaker. Layer 3, HBM, high bandwidth memory. This is the second supply chain that owns the AI industry. An H100 has 80 gigabytes of HBM3 at 3 terabytes per second. A Blackwell B200 has 192 gigabytes of HBM3E at 8 terabytes per second. TPU V7 is in the same neighborhood. Why does this matter so much? Because large language model inference is memory bandwidth bound, not compute bound. The matrix multiplies are small relative to the cost of streaming hundreds of gigabytes of weights through the chip on every token. Whoever has more HBM bandwidth wins on inference, full stop. There are exactly 3 HBM suppliers in the world: SK Hynix, Samsung, and Micron. Today, SK Hynix has the lead. They ramped HBM3E 12 high stacks first and locked in NVIDIA's primary supply contract. Samsung had stumbles on early HBM3E qualification, but is back in the mix on HBM4. Micron is the newcomer, smaller share, but ramping fast on HBM3E and HBM4. Here is the structural reality. Both architectures, GPU and TPU, are memory bandwidth bound. So both architectures are at the mercy of these 3 companies. If SK Hynix has a yield problem, NVIDIA has a yield problem. If Samsung's HBM4 wins the next qualification cycle at Google, the TPU V8 roadmap pulls in. The accelerator designers can ship the most beautiful silicon in the world, but if HBM volume slips by 1/4, every roadmap slips with it. The real winner of the AI build-out, dollar for dollar, is not the chip designer. It is the memory supplier. Layer 4, the system. This is where the architectures actually diverge, and this is where Google has done something structurally hard to copy. NVIDIA's interconnect story is NVLink. Copper-based, electrical, very high bandwidth between GPUs in a rack. The new NVL72 system puts 72 Blackwell GPUs into one NVLink domain, sharing memory coherently. Outside the rack, you fall back to InfiniBand or Ethernet. That cliff between intra-rack and inter-rack matters a lot for very large training jobs. Google's TPU pods do something different. They use OCS, optical circuit switching, at the pod level. Optical, not electrical. Reconfigurable, not fixed. A single TPU V7 pod can scale to over 9,000 chips in one coherent fabric with 3-dimensional torus topology, and the OCS fabric lets Google dynamically route around failed links and reshape the topology for different model parallelism strategies. There is no equivalent of this in the merchant market. Why is OCS hard to copy? 3 reasons. 1, the optical switching hardware is not commodity. Google built it in-house with a partner over many years. 2, the software stack, XLA, the compiler, the scheduler, is co-designed with the topology. Pod scale coherence is not a feature you bolt on. It's an architectural commitment. 3, you only get the payoff if you also own the workload. Google trains and serves Gemini on these pods. The interconnect is shaped for those exact data flows. NVIDIA is responding. NVLink Fusion, photonics on Rubin, Spectrum X Ethernet. All of this is closing the gap. But for the next 2 years, if your training run needs pod-scale memory coherence across thousands of accelerators, Google has a lead that is not about silicon, it is about the system around the silicon. So who wins? Here is the actual answer, with no marketing slides involved. For the next 2 years, through 2027, NVIDIA wins on volume, ecosystem, and revenue. CUDA is the moat. Every major model lab has CUDA native code. Rubin ramps in late 2026 on N3 class with HBM4, and that closes most of the process and memory gaps. NVIDIA's customer base is everyone who is not a hyperscaler-owned AI lab, and that's a much bigger market than the hyperscalers themselves. Google wins on specific workloads, particularly its own internal training and high-volume inference of Gemini-class models. Because of the OCS pod architecture, the JAX and XLA software stack, and the fact that they don't pay the NVIDIA margin. For Google's internal economics, TPU is dramatically cheaper per useful flop than buying GPUs. But the real winner, the one that nobody on YouTube wants to talk about, is the supply chain. TSMC, because they own the leading-edge node in CoWoS-L. SK Hynix, Samsung Micron, because they own HBM. ASML, because they own EUV. These three layers are gating the entire industry. Every dollar of accelerator revenue, GPU or TPU, eventually flows back to them. That is the unsexy structural truth, and it leads naturally into the next video in this series, which is going to be on the foundry and packaging supply chain itself, who is investing where and what breaks first. If this was useful, the best thing you can do is subscribe. I am building this channel into a place where you can get the actual semiconductor industry view of the AI race, not the marketing slides. Drop a comment with the architecture you want me to break down next. Thanks for watching, and I'll see you in the next one.